Aloha, Rich Halverson here, and this is ITS388AL, and this is the second video of the course, and we are going to cover the important topics in Chapter 1. So I'm going to share my screen, and so I've opened up Laulima, and we're going to just cover Chapter 1 right here. So let me okay, here's my here's a online version of the textbook. You you need to purchase the textbook, but you can the 8th edition is out now, so you should be able to get the 7th edition pretty inexpensively. So we're going to cover Chapter 1. Let me show Chapter 1 here, and let's see, the book is organized. It's a real good book. This professor started out in the music or something like that, and then he got an inspiration for computer science, and he's written some very good series of textbooks here. This course, we're covering assembly language, and here's an example assembly language program, and this looks like it computes this expression right here. So we do an add, and then we do a multiply, and then we move some data around. If you look, there's at the end of each section, there's a section review here. So here, for example, how do assemblers work, so on, and in Appendix C, it provides the answers to those section review questions. So if this is a good, it's easy to test yourself and then see how well you're doing along the way. In this, if we go back to Laulima and we look at week 1 here. Here I've indicated some learning outcomes, and these pretty much come from the textbook. And we see that we need to cover, there's 2 assessments. There's a quiz. There's going to be a quiz every week, simple true-false multiple choice true-false quiz. And then there's going to be another test. It's another simple 10-question test, but this one's fill in the blanks. Okay, so it's a slightly harder, I guess. And then there is this programming assignment, which is pretty straightforward. So let's take a look at, and there are a couple of really good videos here that you really should look at, converting between binary and decimal, and hexadecimal and decimal, and so on, and that's pretty important. That'll be important that you be able to do some of that in your head or quickly with a calculator throughout the course. Let's just quickly take a peek at what the first fill-in-the-blank test looks like. And so you have as much time as you need to take these tests. So, what that means is, and you can close the test and come back later, just as long as you do all this before the due date. Now, I believe after the due date, you actually get, if you have not taken it at all, then you get 1 chance to take it, and that has to be done before finals week. So these are pretty pretty well representative of the kinds of things that you're going to have to know about and kind of have to do in your head, but it gets pretty easy, like converting this number to a hexadecimal number. You begin to learn that this is 13, which is about a D. This is A. This is E, and this is D again, I believe. Let me see, hexadecimal. Oh, I made this one up. D, E, A, D. So anyway, and then this is what a quiz looks like, just a multiple choice quiz. I mean a true-false quiz, easy. You only get one chance to take this one, but these questions are taken directly out of the textbook. So it's easy if you want. You can have this quiz open and the textbook open, and you should be able just to go through and narrow down. And you might have to. Here's where we're converting some things around. You're going to have to do a little bit of math. However, you may be able to find online some helpful tools, browser-based helpful tools. All right, so that's what the quizzes look like. What I'd like to do today, real quickly, don't take too much time, is to go over the quiz or the slides that were provided for this chapter. I want to go back to the beginning here. Should have done this beforehand. Probably an easier way to do it. Okay, so chapter 1 basics here. Let's see. Welcome to a virtual machine concept. This is it's kind of important, but it's not super important. Data representation, very important, and Boolean operators is very important. Let's see. So why am I learning assembler hardware software? You can okay. Okay, here's a nice table which describes some differences, some key differences between when comparing high-level languages with assembly language. Let's see how important this is. Hardware device driver. Language may not provide for direct hardware access. So if you want to okay, so these are comparing applications and more or less the appropriateness of writing these applications either in a higher level language or an assembly language. Assembly language, of course, is the lowest level. Above ones and zeros, there's a direct one-to-one correspondence between the assembly language instructions or assembly language programming statements and the bytes of program code in your program. Some applications are much better suited or much better written in higher level languages, and others you cannot write them in higher level languages. Like device drivers, you can't really write those in higher level languages because high level languages don't have access to the ones and zeros that come in off the serial port and so on. This virtual machine concept is kind of an interesting thing to understand. It's kind of a natural thing. We have level 0 languages, which are native machine code, and human-friendly languages we might call level 1 languages. Level 1 languages don't need to be converted to level 0 as a level 0 language because that's how the machine is able to perform to execute the program. That can be done by interpretation or by translation. Translation is when you compile. And so you transform the entire L1 program into a completely translated L0 program. And interpretation does sort of one line at a time. So it takes like one, and translation is usually more efficient, produces faster code because you can do some optimization. But interpretation has many conveniences. So here's an example of how that works. We have a C++ statement, and that gets translated into assembly language. And the assembler translates that into the ones and zeros. You notice these ones and zeros are represented in hexadecimal, and that's why the conversion of 1 0 1 0 0 0 0 1 and so on. These are that's what the translation is. And these are the corresponding. These are the words, or the human interpretation of these. You're moving some value A into the EAX register, multiplying the EAX register by the value B, and so on. And so here is a sort of a hierarchical description of this. We've got the digital logic, which is that's electrical engineering stuff, and then you have an instruction set architecture that is implemented in the digital logic, and then the assembly language, is on top of that, and the higher level language is above that. The instruction set architecture is usually fixed. That's the Intel, it's whatever the chip is, the Intel microprocessor chip is able to implement, for the version it is or whatever. And of course, the digital logic is how that is implemented. But assembly language, of course, the language itself is fixed. But then the higher level languages can change because the translation of the higher level language down into the assembly language, that's just software. Those are the compiler writers, the people that write the compilers. And so these higher level 4 languages here are, these languages which we're used to. And then assembly language is what we're going to be learning about. So that's all interesting. Data representation is a much more important part of this chapter. We're going to have to learn about binary numbers, binary addition, the sizes of integers, hexadecimal integers, and translation between decimal and hexadecimal, signed integers, whether or not you're going to represent negative numbers or not, and then storing characters. So binary numbers, as you know, are 1s and 0s. The MSB is the most significant bit. LSB is the least significant bit. So in this number right here, this is the lowest significant bit and this highest significant bit. That's the same way that we write base 10. When we write the number, 546, the 5 represents 500, which is on the left, which is the leftmost, the most significant bit, digit, and then the 546, the 6 is the least significant digit. And so, this is each one of these bits. Instead of, in base 10, it's 2 to the 0 and 2 to the 1, 2 to the 2, 2 to the 3. I mean, in base 10, it's 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. In base 2, it's just 2 instead of 10. And so these values here are values that you should try to kind of memorize if you haven't already in your life. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. 256 is important because it's 2 to the 8th. 4096 is important because that's 3 bytes. 32,768. The next one is 16,384, which is 2 to the 16th, which is 4 bytes. So here's translating binary to decimal. And if you go back to the, you can watch this video here. He does great videos, and you watch that and you can see graphically how that works. And unsigned decimal to binary. So this is how you convert from decimal to binary. You keep on dividing by 2, saving the remainder. That sounds like the mod operation. So you keep on doing mods, where the mod, the remainder, that's the digit that the next digit that you have figured out, and then you keep on, and then you do the mod operation on the quotient, on the remaining quotient, and you continually do that, and you end up with these remainders. And if it's mod 2, it's only going to be 0 or 1, and so the remainders end up being the digit. So this converts 37 into let's see, this is the highest order digit. Well, it shows right down here. First you get the lowest order digit, then the next order digit, then the next order, next order, next order, highest order. So 37 ends up being this number. All right, so binary addition is also important. And it's easy. It should be, think of it as easier than decimal addition because you know, 0 plus 1 is just 1, 0 plus 1 is 1, 1 plus 1 is 1, 0, carry the 1, so it's 2. 2 is like, looks like 10, so 1 plus 1 is 0, carry the 1, and then you know, 1 plus 0 is 1, and then these are all 0. So it's pretty easy to add in binary numbers. We store integers in you know, series of bytes, either 1 byte or 2 bytes or 3 bytes or 4 bytes. And 1 byte is 8 bits, 2 bytes is 16, 4 bytes is 32, and 8 bytes is 64. And you might recognize all these numbers. These are all powers of 2 and so on. And these here are the ranges. And so 16 bytes, I'm sorry, 16 bits can hold up to 2 to the 16th power, which is 65,536. So it's 0 to 65,535. And you'll notice that 2 to the 32 is about 4 million, or 4.2 million. 2 to the 64th is some much larger number. So you should, so what is the largest unsigned number that can be stored in 2 to the 20th? In 20 bits, well, it's 2 to the 20th power, which is a little over a million. It's 1 point something million. You can figure that out on your calculator. And so the conversion from hexadecimal to decimal is straightforward. It's you know, you can just count the binaries 0, 1, 2, 3, 4, 5, 6, 7 all the way up to 15, and those just are, you know, from 0 to 9 it's the same, but then after that we have, you know, we need some more digits because we're going, it's base 16, so we need to have something for from 9 to 15, so we use A, B, C, D, E, F. But because hexadecimal is 2 to the 16th and binary is 2 to the 2nd, it's a power. It's easy. The translation is real easy and direct. And so all you have to do is remember that you know, B is 1011, C is 1100 with D, E, and F, and you can kind of remember those in your head or figure them out. And that's how you translate from back and forth from binary to hexadecimal. And then once you have hexadecimal, then you can translate to decimal. You know, you can have a calculator. You can easily do that. But you know, entering in binary can be tedious and you can make a mistake. But entering in hexadecimal, you know, wouldn't be. So this is how that translation would work, as you see. How to translate this into hexadecimal is pretty easy. Just group them up in groups of 4. This is the math for computing from hexadecimal to decimal. And these are the powers of 16, are kind of good to know. Converting from decimal to hexadecimal, division. You're not ever going to have to, you know, today we use a calculator, but you really need to understand what's going on because it gives you the insight and understanding when we start debugging programs. You know, you're going to write a program, you're going to wonder if it works, and all you're going to be able to do is look at a bunch of hexadecimal digits and conclude whether or not it works. So that's why, and you know, you'll have help, you know, paper and pencil and so on. Hexadecimal addition, it's the same thing. You know, A plus B is really 10 plus 11, which is really 21, which is 1.5 in hexadecimal. The value 21 is 1.5 in hexadecimal. So it's a plus b is 5 carry the 1. See, so anyway, interesting. Subtraction, you do this, you subtract, and you may have to borrow from the next higher digit. So the way signed integers work is that there's two things. One is that there's the highest order bit is a signed bit, and if it's a 1, it's representing a negative number, and if it's a 0, it's representing a positive number. And so you see, instead of when you have a signed bit, then the range is still the same. It's 255 or 256 range, but we're going plus and minus. So you can think of it like you only have 7 bits. 7 bits is 2 to the 7th power is 128. So it's like minus 128 to plus 127. If this is 0 and all of these are 1s, then that's representing positive 127. That's the highest you can go. And now, some computers way back in the olden days would just have the sign bit, and so to represent, minus, this is A. 1010 is A, or 10. If you had a 1 here, it'd just be minus 10, but that's not how we learned very quickly back in the 50s that 2's complement was much better, much more efficient. And so the way that works is, first of all, you reverse all the bits, and then you add 1 to the whole thing. So let's say you're starting out with this number. This thing is just the value 1. Well, you reverse all the bits, and you get this, and then you add 1 to it, like this, and that ends up being this number. And so this is minus 1. This is the 2's complement representation of 1. So this is minus 1. And so you want to be able to take plus 1 and minus 1 and have it equal 0, and it does. So you want to be able to add a negative number to a positive number and get the right answer. So 2's complement notation is the way to do it. Binary subtraction, and how to, okay, so you need to know how to do these things. Form a 2's complement of hexadecimal, convert sign binary to decimal, decimal to binary, decimal to hexadecimal, and hexadecimal to decimal. And you should know the ranges. And this is converting, this is when it's representing characters, where you have bytes representing characters. And there's different character sets. There's regular ASCII, extended ASCII, all the way up to 255. And see, Unicode is 2 bytes. That's why 0 to 65,535. Yeah, that's 2 to the 16th minus 1. And then you also, this other way of doing it, where you just have a bunch of bytes in either Unicode or extended ASCII. And then at the very end, there's a null byte, which is like all zeros. And so there's no character that represents all zeros. All zeros is the null byte. And so that way the string can be any length. Using the ASCII table inside cover of the book, inside cover of the book, this ASCII character set. Oh, and then, no, where's it? This ASCII. This is extended ASCII. This is regular ASCII. All right. Let's binary ASCII decimal. So this is where, ASCII decimal, and we'll get more to that later. Okay, Boolean operations. This is the last important thing that you have to know how to do. Nots, ands, ors, operator precedence. There's operator precedence down at this level also with Boolean. And truth tables are very interesting, but it's hard for me to think of a case where you're actually going to need to create a truth table to figure out the solution to something. If you're implementing the digital logic to implement an instruction set architecture, you work with truth tables all the time. But so that could be why. So with Boolean algebra, here's the sort of the symbology. This is not x. So it's remember, in x is going to be 0 or 1, and so not 1 is 0, not 0 is 1. That's how you represented. For anding, it's they both have to be 1 for x and y to be 1. It uses an upward arrow. It looks kind of like an A without the bar. And then OR is just one of them has to be 1 before this thing evaluates to a 1. And if you have something like this, not X or V, the unary, the not always was applied first, unless you put parentheses like this, which means something different. And in this case, you do the not Y first, and then you do the AND. So that's why. These are gates. When if you're designing the digital logic that implements the instruction set architecture, you would be using a NOT gate. You'd be using AND gates. You'd be using OR gates. This is operator precedence. In this case, first you do the NOT, then you do the OR. In this case, first you do the OR, then you do the NOT. In this case, first you do the AND, then you do the OR. Here's an example of a truth table where you may want to figure out what the solution to this is. A truth table is convenient for that. You put X and Y, and then you put all combinations of X and Y. That'd be false, 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 true, true, false, true, true. Those are all the combinations of X and Y. And then you just figure out, and you just make more columns to figure out what each thing is. And so you want to find out what not Y is. So you create this column here, and that's just the opposite of what X is. And then at the very end, you do the OR, and so that's this and this. And T or F is T, T or T is T, F or F is F, F or T is T. So that's truth tables. This is a multiplexer, and the way a multiplexer works is, I'm going to switch over to, end sharing, and I'm going to move this over to this computer. And I'm going to share again. Let's see, where's the, I guess I need to put this here. And I need to put this here. And let me share this again. This time I want to share this screen. Okay. And so the reason I wanted to use this screen is because I have a nice pen here. And let me go like this, and this. And let me just make this, can I make this bigger? No. I guess I need to do, how do I make this bigger? Let me turn that off first. Go like this. Okay. I wonder if this is going to work. All right, so that's fine. Now let me go like this and like this. Let me make it, I guess that's okay. All right, is this? Okay, good. All right, so this is a selector. Oops, S-E-L. Let me erase that. Okay, this is a selector, S-E-L. And this is going to be either a 0 or a 1. When it's a 0, then X transfers through and goes out Y. So this is a path. It creates a path here. It's just 0 or 1, but it's a path where X gets passed out to there. That's if this is 0. If this is a 1, then it's not that X, it's can I change colors? Cool. It's this one. So if it's if this is a 1, so you can see that this is like a selector. It selects 0, 1. 0, 1 is going to select whether X gets passed through to Y or Z, or Y gets passed through to Z. So there's so we have 3 inputs, 1, 2, 3, and so that means the truth table is going to have 2 to the 3 is 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have to put all the combinations of X, Y, and S. This is S. This is X, Y. And it's FFF. It's all the combinations here. This is not the way I would write it, but it doesn't matter. The order doesn't matter. And then you just start. This is the expression. This is the logic that implements this multiplexer. And so you see, what we want is that when S is false, in other words, when it's 0, we should see X. So here's when it's 0, and we should see this should be the same as this. This should be the same as this. This should be the same as this, and this should be the same as this, and it is. And then when we do the T, the true, then this one should be the same as this one, and this one should be the same as this one, and so on. So that's how a multiplexer works. And okay, so and the reason I went through that is because there is a question on one of the tests or quizzes or something where it's how many bit. Let's say you have a 4-input multiplexer. Let's say you've got something. Let's see, I can do something like make this white. Let's say you have a multiplexer. Oh, look at that. And it's got 4 inputs. 1, 2, 3, 4. How many selector inputs do you need? For 2, you just need 1 selector input. If you have 4, how many selector inputs do you need? And that's a question on something. All right, let's see. So are we done with the slides? Yes. All right. So let me see where. Let me stop my sharing here. And let me put this back over here. Let's see. I need to put this back down here. All right. So okay. So I guess that's about what I have for today. The important parts of what I've covered are the binary arithmetic part and the conversion between bases part. Those are the 2 things that you're going to have to know throughout the semester. And so try to pay attention to those. And I will see you at the next video. Thanks for watching.